Hi guys, so a few more questions about lenses, and those questions tend to be kind of tricky. So here the first question is how to find the focal length of a converging lens. So that you know that I did a demo, that's easy. You take a magnifying glass, that's a converging lens, right? And you place white paper underneath, that will be your screen. And then you have an object that could be the lamp very far away or the trees outside the window. And you're going to move your lens until you get a neat image on your paper. And that distance here will be the focal distance. But you cannot do the same thing with diverging lens, because when you have a diverging lens here, the image is always virtual. So you cannot have a screen. Nothing will show up on the screen, right? So it's not going to work. So you cannot use the same method. So that's not going to work. And if you have a second diverging lens, that's not going to work either, because you're going to still have a virtual image. Um, Diverging lens do not have a focal length. That's not true. You see here, you do have a focal length, such as a ray that is parallel to the optical axis here. So let's say it's like it's coming from very far away. It's going to be diverging out like it's coming from the focal point. So the D is not right. So the answer has to be C. So we use a converging lens of non-focal length to find the focal length of the diverging lens. So let's see, I have a picture somewhere here. So you will do a setup like you see here. So you have a diverging lens. Let's say you don't know its focal distance. And then you have a converging lens and you do know its focal distance. So you have the object. You use an object here. First step, you're going to get a virtual image here, right? Because of the diverging lens that you cannot see with your eye. However, the final image, so that will become the object for the converging lens, and then you have your final image here. So you will walk backward, right? So if you know where is that image here that you get, that it's real, that you can display on the screen, okay? So you know the distance of that image, and you know the focal distance here, of course, then you will know where is the virtual image here, which is the object for that lens. So you know that here, and you know the distance of the object relative to the diverging lens. So you know the image for the diverging lens, you know the object for the diverging lens, so you can find the focal length of the diverging lens, right? It can have a very nice diagram. It explains it very well. And maybe you can do that experiment, right? If you have someone who is like me, nearsighted, you can take the lenses here. It can take a magnifying glass and see if it works, right? Make your own compound system. Converging lenses are just magnifying glass, so they are very cheap. You know, you get to a dollar stores, you go to a dollar stores, you can find them um, easily. So that was for the answer. That will be number 28. So the answer is C. So 29. So you need to know how a microscope works. So I found like a website here with a, I don't know why, no, I lost my website, but sorry, so I saved the image here somewhere. Here. I will write down the video, the website. So that's how a microscope works. So you see you have two converging lenses, so two convex lenses. So you want to have the object here as close as possible to the focal point, but not inside. Because if you place it inside, then you're going to have a virtual image. So you want that as close as possible. And then you will get an enlarged real image upside down, but enlarged because that distance here is smaller than twice the focal length. So that's going to be enlarged. And then with the eyepiece here, then you're going to get a virtual image. So this one will behave like a magnifying glass. And the virtual image your eye can see. Okay? So with a microscope, you need to have the object as close as possible to the focal point, but not inside, but as close as possible. With a telescope, then the object will be really far away. So that's how a microscope works. The final image is virtual, upside down, but it doesn't matter because we have another converging lens here. So it will make that image here. Virtual image will be projected on our retina here. So the answer is B, just outside the focal point of the objective. Okay, so that's right, number 30. So it's just a review. It's a review of about lenses. So what's happening when white light passes through a prism? Light with the greatest speed is refracted by the greatest amount. Now that's not true because it's red. Red has a larger speed than blue, and red is not as much refracted than blue. It's the opposite. So blue will have the smallest speed, and it will undergo the greatest refraction. Highest frequency is refracted by the greatest amount. That will be true because blue is refracted more than red. Lowest frequency is refracted by the greatest amount. No, and then no. So remember we talked about dispersion. So if you have like prism here, you can see the picture there, right? So you see that blue will be refracted more than red. I think I'll already show you that picture here. You see that violet, the wavelength is the smallest, so it has the highest frequency, smaller speed, the speed will be the smallest, the speed of light for violet will be the smallest inside the medium. Red will have the largest wavelength, the smaller frequency, and the largest speed inside the prism. And that's how you get dispersion. And of course, we talk about that, but denser is the medium, more refractive power you will get. Okay, so here I cannot see very well. So number 31. So here you have a compound system. A virtual image cannot serve as a real object. So it's kind of confusing here. What they mean is that can you use a virtual image as an object for another lens? And the answer is yes, right? That's what we saw. We saw that here, right? So you have a virtual image here because of the diverging lens, and that virtual image will serve as an object for the converging lens. So that's what they mean. So that's not true. A real object will always form a real image. That's not true, because a real object can of course produce a virtual image. And then light must travel through lens 1 and form an image before it travels through the second lens. So we talk about that. That's not true either. So the answer is D. Okay, so about that third answer here, remember, if you have um, two lenses like this, for example, you see it's gonna go through both lenses, and then it's gonna be making image 1 and then image 2. So light goes through the lenses first, right? And then because of this one, it's gonna make this image first, and because of that one, that will become an object for that one, and you have the final image here. Okay, I know I used to have other example. I don't know if I can see other example here. Here is the same example here. We have two lenses, so light will go through those two lenses here. That will be the image from one that will become the object for number 2. That's going to be the final image. Same thing here when they are close to each other. So that's why the final answer is D. So here they talk about a telescope, and you can read the question. Now, remember telescope? We talked about telescope before here. We have a telescope there. So the idea is the objective is always a thin lens. It has to be a thin lens with a large focal length. Okay, so that way you will get a real image, but that you cannot control the location of the object. Okay, all the object that you see through a telescope will be very, very far. So you cannot, go close to a star, such as the object is inside twice the focal length. So all the objects have to be very, very, very large. The only thing you can do is to get a thin lens, and if you get a thin lens, you will get a larger image. And then you have the eyepiece, which is basically a magnifying glass. That image here will be inside the focal length of the eyepiece, so you get a virtual image but enlarged. So I can show you that here. If you take a converging lens, like very far away, you see that will be the image. It's a real image. It's upside down. It can be displayed on a screen. If I make it thicker, if I take a thicker lens, you see that the image gets smaller. If I take a thinner lens, right, with a large focal distance, I get an image bigger. So that's why you want the objective to be a thin lens, I mean small, not very thick, so you get a large focal length, right? So that's the idea behind a telescope, right? So you want a large focal length for the objective, small focal length for the eyepiece that will behave like a magnifying glass. So you want a convex lens with a focal length that is very long. Yes. Okay. So this question here, So this is math, which I think is easier than those conceptual questions. Those conceptual questions sometimes are not that clear. Always. Not always very clear. So you have convergent mirror. It's a mirror, right? So it means it's a concave mirror, right? So we're talking about a concave mirror. So here we have the mirror here. So here they both have the same size. If I get closer, you get larger, it's upside down, it's real, and it's enlarged. And if you go inside, it's beyond, okay, it's on that side, and it's much bigger because it's virtual and upright. So for a mirror, you're going to apply the thin length equation, the same equation that you use, and it's convergent, so it's concave. That means the focal length is positive, and it's given here 0.3. So I'm going to put everything in centimeter. And then in magnitude, the image is 3 times the object. Okay, so it cannot be this answer here because that's smaller than 0.3. So you will get a virtual image. It cannot be this answer here because you see this is already twice the focal length. So in that case, it's not going to be magnified. It's going to be the same size, right? So if you have your object here, twice the focal distance, which is equal to the radius of the curvature, you see it has the same size. So already you can eliminate some answers. Okay, so then you solve for that. So that's going to be 1/3 times the object. So d sub O plus 1/d sub O equals 1/0.3. So you just do the math, right? Well, 3D equals 1/0.3. So you can solve for that. So 3D equals, you cross multiply, divide, so 3D equals 4 times 0.3. So D equals, we divide by 3, that's going to be 0.4. Okay, so that's going to be the answer. That will be answer B. So at least here, at last, we have an easy question. So which one are consistent? So that's definitively not it, because it has to be refracted. That's not it. Here, what you see here is like the normal. So instead of going with straight line, this has to bend toward the normal. So that's a no. This is a no. So we are left with 1 and 5, which is the answer A. Which is the answer A. So here we are missing part of the answer. What is not true for visible light? That is possible, right? When electron goes from a higher level of energy to a lower level of energy, it's going to burp out photon, and the photon can be a visible photon. As the wavelength increases, the frequency decreases. Yes, that's true. They are inversely proportional. visible light has higher energy than electromagnetic wave or radiation. That's true. Microwave. Let's talk about microwave. Yes, that's true because you have UV, visible light, infrared, uh, microwave, radio wave. So microwave have less energy than visible light. So we are left with D. That's not true because here it says wavelength between 200 nanometer and 400 nanometer, but that's not true because if you look at the visible light, I think I had that here. Visible light, you see the wavelength goes between, I don't know, 500, say, and 800 here, and maybe 400, so 400 to 800 nanometer, and not between 200 and 400. So 200 and 400 will be here, and here will be UV. So this is UV light. So when a parallel ray goes through a glass lens, the ray all meet at the same focal point? No, because you remember if it's white light, we can have chromatic uh, aberration. So it means that blue light will bend more than red light. So they are not focusing at the same point. Is the same for all colors? No, because first of all, for blue has more, you see blue here has more, is more refracted, so index of refraction is more. The focal length for violet light is smaller. That could be it. All have the same focal point, depends on whether lens is converging, diverging. No. So C, right? Because violet light will refract the most. So that means, as you see here, the picture I just show you here, you see that the focal point here for violet or blue will be smaller. The focal distance here will be smaller than the focal distance for red. So the blue light will refract more than the red light. Okay, that's it for today.